All right, hey guys, I'm going to do another Leetcode question. So we're choosing an easy one. I'll pick one at random and start the timer over here. And let's see what we get. Okay, number 728, self-dividing numbers. I'm using a Google Doc over here. I've just made the size a little larger. Google Docs and notepads and all this stuff suck, but sometimes that's what you get in an interview. You don't have access to a nice IDE with syntax highlighting and all that stuff. So as tragic as it is, you should get used to using a notepad for those occasions where you're getting interviewed in that format, especially like say you have a whiteboard or something, which maybe not as much for entry-level interviews, but once you start doing maybe in-person or on-site interviews, there's going to be a whiteboard at some point, especially if you're more on the math or algorithm side. So just kind of get comfortable with not having access to these tools. Let's see what we got here. So self-dividing numbers. A self-dividing number is a number that is divisible by every digit it contains. Oh, that's kind of cool. So number 128 is a self-dividing number because 128 is modulo 1 is equal to 0, modulo 2 is equal to 0, and modulo 8 is equal to 0. It's not allowed to contain the digit 0. All right. Given two integers left and right, return a list of all the self-dividing numbers in the range, left to right. That's kind of cool. So here from left to right, the range 1 through 22, you iterate through all of the values, checking if that number is self-dividing or not, and then return a list of all those values. So I guess here left and right promise to always be left smaller than right, both of them bigger than 1 and less than 10,000. So that gives us some nice constraints. It'll always fit in memory. I'm trying to think about the ideal case. It'll be O of n time, I think, for n values between left to right. Is that true? I wonder. I wonder if there's some fun little binary or mathematical thing one could do to check if numbers are modulo, like divisible by those digits within. For example, even numbers are always divisible by 2. And so if an odd number had a 2 in it, like in the second digit or third digit, it's never going to be a self-dividing number. So just kind of talking out loud. So let's say we had the number 134. This is not... Well, that's not actually correct. Never mind. Yeah, sorry. If we had an odd number that has a 2 in it, that'll never be modulo 2 is not equal to 0. And that there's a 2 in this digit. So we can never have an odd number have a 2 in it. And I'm just trying to think about whether that gives us any advantages in terms of how we reduce this list. Because we kind of get whole swaths of numbers that are always going to be illegal. But I can't think of it just yet. So let's just kind of talk our way through some of the potential approaches. So approach 1, what I'm thinking about is having some sort of magic function, we'll call this like is self-dividing. And we give it a number, which is an int, and it'll return a bool if it is or isn't. And it iterates through int the digits, checks modulo, returns false if any fail, returns true otherwise. So that's kind of how that logic would work. And this would be O of k for k digits in a number, because here modulo at least is O of 1. And then our main loop is going to be like, they call it self-dividing numbers here. And we get ourselves nums, which will be a list of ints. And, oh, sorry, we get our left and right, I think. Actually, left, which is an int, and right, which is an int. And our output's going to be a list of ints. And kind of the way we could do this is return the array of numbers. Num for num in range left to right. Is it inclusive? Left to right inclusive? Yeah, it is. So +1. if self-dividing. And we're just doing an inline for loop here, basically, where it's filtering this range from left to right inclusive for values where self-dividing is true, and it returns only those numbers. So this is kind of one way we could approach this. This becomes O of n for n numbers between left and right. Actually, kn, O of kn, for n numbers left, right, k digits, a number. That is how this approach would be. I wonder if we can do better than that. I'm not entirely sure. It feels like we should be able to. I wonder if there's some fun binary thing. So here's what's coming to my mind. I'm thinking about if you guys have ever heard of the sieve of Eratosthenes, the prime sieve algorithm. I'm probably butchering that pronunciation completely. But instead of trying to find prime numbers by checking if each number is prime, you take your array of numbers and you just remove any of them where that number, where there's a number, like you just take the number 2 and you just check, you take 2 times 2 and 2, and you just keep going through that array and throwing out all the even numbers. Then you do 3, all the numbers multiples of 3, and you just do that until you reach the square root of the length of the array, and you've got all your prime numbers left. And I'm wondering if you can do something like that here, but that would still be O of n. And yeah, it would be O of n. It would still be O of kn at the end of it. So I don't think a sieve makes sense here. Okay, we're about 6-7 minutes in. I think I'm trying to think of any other approaches besides that. I can't see how that one works. Can't see how this works better than O of kn. So skip. This is O of kn time and space. Though technically O of n space if we're ignoring the number of digits in a number. So I think this is close to optimal. I think you have to... Do you have to check every single number? Maybe there's some way to know the next self-dividing number without having to check every single number in the range, and I just don't know what that is yet. So maybe the interviewer might give a hint for how to approach that, but what I might say is, let's say the interviewer is okay with starting with this, so let's just implement this and continue that way. So how would we iterate through the digits? The easiest way I can think of is to divide by 10 every time and check that specific digit. So while the num is greater than 0, 1, and also we're not guaranteed that there's no 0 in the digits. So while the number is greater than 1, if num what I'd like to do here, what I'm trying to do here for, let's say, the digits 1, 3, 4, I want 4, then 3, then 1. So kind of what I'd like to do is somehow take 134 modulo 10, and that gives us 4. And then we divide it by 10, and that gets us to 13. Then 13 modulo 10 gives us 3. Then we divide that by modulo 10 gives us 3, and then that divided by 10 gives us 1, and then 1% 10 equals 1. We kind of go along these lines, and then we can check with this 1, this 3, and this 4. We also want to check that it's never 0. Check never 0. And finally, at this point, we take 1 divided by 10, and that equals 0. And we're done. So what happens if we had a different digits? Let's say we had 10, or yeah, let's just do 10. First we do 10 modulo 10, or even 20 just to be something else, and that equals 0, so fail out at this point. Okay, yeah, so we can do that. Similarly, let's say the number was 203. 203 modulo 10 is 3. 203 divided by 10 is equal to 20. 20 modulo 10 is equal to 0, so fail out. Yeah, okay, so that should be our main logic of how we're going to be iterating through the list. So while the number is greater than 0, digit is equal to num modulo 10. And then if that digit, if num modulo digit is not equal to 0, return false, because we always want it to be. And also, if the digit is equal to 0, if digit equals 0 or the number modulo the digit is not equal to 0, then we return false because it's no longer self-dividing. And then after that, we set the number to be equal to the number divided by 10. And so you could just do, I think, like that. And then finally at the end, we return true because you passed in your self-dividing. Okay. I think that gives us our main logic. So we're at about 12 minutes in. Let's have a look at this function. Still O of k for the number of digits. We're just dividing down by 2. And self-dividing, this is just a O of n through the range left and right. So let's put this one in here. And then we have to also pass in the main function. And part of the reason I created a separate function is just so I could do that inliner. Like here. And we also need to turn this into a class function. And that way we can just do self.isDividing. Okay. So we're getting the digit by moduloing it with 10. If that digit's 0, or the number modulo that digit, it doesn't self-divide cleanly, then we return false. Self-dividing. Finally, we divide that number by 10, going down the range, and return true otherwise. And then we just do this range from left to right inclusive, and keep only the numbers that are self-dividing. So I think that should work. Let's try to run it and see if it passes the test cases. Oh, we need to fix typos. True is capitalized. Trying to think of any other ones. False is capitalized, true is capitalized. Let's have a look at that. Oh, never mind. Completely wrong. We got 21 when we expected 21 to not be in there. So why did 21 work when 21 shouldn't have? Well, let's have a look and see what happens if we put in 21 to this function. So first of all, 21 is the number, and it's greater than 0. Digit equals 21 modulo 10 equals 1. Oh, we are checking with the number that's being divided by 10 every time. We need to use the original number. So let's say num equals num here. Well, that's important. Good thing we recognize what that is at least. So I'm going to copy that over here actually. So while num and num is equal to num, OG number, original number. All right, there we go. So here now we're checking with the original number that divided by the specific digit is equal to 0. We're cutting down that number with a copy of it rather than the original, because that's what we want to make sure the check is with. All right, so that seems to pass for the test cases of these two. That's good to see. Let's submit it and see what we get. Okay, and passes the submission, which is great to see. We're in the main ballpark of the solutions. This kind of suggests to me that there aren't any... If there was a mathematical solution, I would expect the final solution to be like all the way over to the left in like less than 10 milliseconds. So the fact that we're not seeing that kind of tells me that we might have gone close to the optimal approach here of O of kn or O of n, depending on how you look at it, which is good to hear. I'll have a look at the solutions another time, but we're about 16 minutes in. Thanks for watching, and I hope you guys were able to follow along, and let me know if you can think of any tricks or tips for this question, and see you guys next time.